craft forward. That is a quite simple thing. So we have 4 steps, yeah? Ingestion, compression, expansion by applying heat, and exhaust. Those are the 4 steps. The same like in a piston engine happened here in our gas turbine engine. Important is also in general, yeah, when you have a rough, yeah, when we say, okay, we have several sections in our engine, yeah. Of course, we have our compressors, the intake as can be seen here. We have our combustion section where the working step cycle itself takes place, yeah, conversion, yeah, from potential energy to kinetic energy. And then we have our turbines and the exhaust. Please bear in mind, yeah, and you will remember probably the 2 sections. Every gas turbine engine has been separated in 2 sections. Cold section and hot section, yeah? Where does the hot section start? You still have this in your mind? Oh, no Sultan also. How many we are now? Sorry to interrupt, but no Sultan is writing me. What? Where's Bulat? Sorry. Hello, no Sultan. And he should just by. You just logged in, yeah? You made the click or the link in the email, correct? Because it seems that Bulat has some problems. But just by clicking. In the email. Let's see. So go ahead. Yeah, I go ahead. Yeah, so in general, yeah, if we divide the engine into the sections, we have our cold section, which is of course the compressor and the intake. And the hot section, please bear this in mind, starts with the combustion section, followed by the turbine and the exhaust. Let's talk about hot and cold. Of course, if we say the compressor is the cold section, some kind of tricky because compressors of today easily reach 600 degrees and more just by compression of the air. So it's some kind of hot, yeah, but as stated, not hot enough. Yeah. So cold section, hot section, where does it start? Good. So another thing, yeah, turbojet engines, those are the first ones I can remain here in this sketch, yeah. Of course, there's been a development in the engine build and engine construction. The first ones that have been invented were pure so-called turbojet engines, meaning we had one stream or one intake of air, yeah, not separated whatever, that goes through the complete engine, will be compressed, mixed with fuel, yeah, and so on, and then goes through one exhaust, pure jet engine. Of course, fuel gets, Bulat, good morning, no, good afternoon, whatever. So everything is nice. Now, 2 streams, they also separated the compressors, but I come to this later. Yeah. So then next step was, of course, now, yeah, the industry realized, oh, it's more fuel efficient with the bypass engines, so we must do something to enhance the bypass ratio. And this was the next big step in the evolution of engines when they invented the high bypass engines. At this time, developed in about the 70s, they reached a bypass ratio of 6 or 5 to 1, meaning, let's remain 6 to 1. 6 parts of air will be guided around the engine, stay cold, the secondary flow or the cold stream, and the 1 part out of 7, the bypass ratio 6 to 1, will be guided through the engine and do make the engine run. So, and this part, of course, is the toughest one. We have to compress those and then add fuel and accelerate by applying heat, whatever. But it made the engines more fuel efficient. High bypass engines. You got the idea, I think. Now, with the very high bypass engines, we have 2 thrust sources. The pure jet engine had just 1 source of thrust because 1 stream. Now we have 2. And the higher the bypass ratio, the more thrust will be provided by the cold stream. As you can see here, older engines, I think you still have some of these, with a 6 to 1 or maybe also. Do you have G90 engines in your fleet? I cannot recall, because the engine G90 has about 9 to 1, I think, bypass ratio. The Dash 80C engines from GE and the PW4 engines, they have still 6 to 1, as far as I can remember, bypass ratio. So, and the next step into the evolution, which is, you have this, I have seen in your facility. Let me check here, Those are the ultra high bypass engines. And so again, the bypass ratio has been more enhanced, and you have the PW11 in your fleet, I know this. This engine has a bypass ratio of 12 to 1, meaning, 12 parts out of 13 will stay or remain cold, just will be accelerated, whilst 1 part makes the engine running. And this is actually also the critical point, because this little poor 1 part of air, compressed, heated up, accelerated, has to make the 12 parts to be accelerated. It's some kind of critical. And as you can see here also, they started to invent, that's quite early in the 70s, the 2 or more shaft or system. And do you remember why we had several shafts? So we had an HP high compressor, or no, so we had the core engine with our high pressure system and the low pressure system. One reason was the avoidance of stall, because if you want to build bigger engines that produce more thrust, you need to consume and accelerate more air. So, but the point is, I can show it here. This is a point of interest. This is the last stage of the compressor. And here we would like to achieve a certain compression ratio. So big mass of air, very highly compressed. But if you want to consume more air here, the first stages have a bigger diameter, and you cannot turn them with the same RPM. Otherwise, you would exceed the speed of sound. You will also remember speed of sound and divergent, convergent, Bernoulli's law. Just keep it in your mind or remember how a fluid, a gas behaves if it's going to be accelerated. We have our 2 pressures, the dynamic pressure and also the static pressure. And if a fluid enters a divergent shape, what happens? The kinetic energy, the dynamic pressure goes down. And if the dynamic pressure goes down, the static pressure goes up. So, different in the convergent shape, where we accelerate. So the kinetic energy, the dynamic pressure will be enhanced. And if you enhance the dynamic pressure, the static pressure goes down. But this only is valid for the speeds below the speed of sound. So in case the air itself should exceed the speed of sound, it goes 180 degrees opposite. Yeah, so that's also the reason why you have to take care that the speed within the engine is always below, slightly below the speed of sound, because we cannot change, the shapes of our and within the compressor section and also within the turbine section. Yeah, always be below the speed of sound. Yeah. So coming back to the high pressure, to the high bypass engines, and when you compare, maybe you have an older bypass engines with maybe 5-to-1, and you have a pure jet engine. And the point is, both create their thrust by having a certain mass of air accelerated. So of course, it's much easier for a high bypass engine to gain a certain thrust because it has a big mass of air. And therefore, since it's a multiplication, you don't need that much acceleration. So if you have a jet engine, what do you think? How to achieve that a jet engine gains the same thrust as a high bypass engine? What would be the solution?
More acceleration.
Of course, it's quite simple. Force is mass multiplied by acceleration. And if you have a little small jet engine, you have to enhance its acceleration to get or to gain more thrust. So this is clear, and it's also logical from my perspective, and you know this already, correct, perfect, So coming back to other engine types, there are several ones. Do you remember? Sorry, do you remember which was the most fuel-efficient engine type?
Turboprop.
Yes. Why? There must be a reason, because turboprops, you gain turboprop engines of today, they gain a pipe pass
but
ratio.
If they have 0.6 of Mach.
Yes, depending on the speed you travel, you're right, But the biggest point is, or the best point is, must have its advantages. We have a bypass ratio up to 100-to-1, so very, very high bypass ratio, and that makes the turboprop engine most effective at low speeds, as you said already, 0.6, 0.7, depending a little bit where you read it, and the handout is mentioned 0.7 is the speed. Unfortunately, you're not able to travel in a very high altitude, but in general, due to the low weight, and the low fuel consumption, the engine has an advantage. You please bear this in your mind, And also, since those gas turbines of turboprop engines, which are mainly free, gas turbines, so they can turn in their optimum RPMs, the time between overhaul is also very longer than normal gas turbine engines. And this makes turboprop engines very attractive for airlines, depending, of course, from the aircraft type, and the where they want the flight profile, with maybe not so much range and maybe not so high in altitude, and depending on the city and the amount of passengers also too. So low weight, we have a less fuel consumption, and since the gas turbine engines are not so, let's call it stressed, you have a longer period between the necessary overhaul, of course. Yeah. So let's go on here. Yeah. So we have now our ultra high bypass engines. Here. Yeah. Yes, the guys from Britain, they tend to, yeah, they said, okay, yeah, two shaft system. I got a high N1 and N2. It's not enough. Rolls-Royce, especially Rolls-Royce, yeah, made the decision to build those three spool or three shaft engines, which is an advantage because in theory, every compressor stage should need or should get its own RPM in order to be on the aerodynamical side, yeah, in an optimum range of RPM. But of course, this is not possible because then you have a lot of bearing compartments. So three shaft system or N3 shaft system is the maximum what the industry did achieve. Meanwhile, yeah, they work. Do you have any Rolls-Royce engines? I have forgotten. You have Rolls-Royce engines in your fleet? I'm not quite sure. Yeah. No. Ah, okay. So you're lucky. Yeah. Good. Turboprop engines. We did it already. Let me check here. Yeah. About 100 to 1. Yeah. And this is, of course, a big advantage. Yeah. The higher the bypass ratio, the more fuel efficient engines are. Yeah. Of course. So that's a good example here. And what you can see also, yeah, that the gas turbine itself is quite small. And if you act with a so-called free turbine, we come to this later, the gas turbine itself can turn in its optimum RPM range. So, and that makes those engines more effective and they last longer. Yeah? This is the idea. The principle of the gas turbine is the same. There's no big difference. But yeah, one thing here, since we see it, we still have an exhaust. You will probably remember, yeah, engine types and what do I drive, yeah. Let's stay with the gas turbine engines, regardless if it's a jet engine or a high bypass engine. All we need, or our intention is to produce thrust by accelerating a certain mass of air. So now with these turboprop engine, what is the idea here? Do we really, or the gas turbine itself, what is now the purpose of the gas turbine? Do we provide just thrust by the air? No, yeah? You remember we now have to provide torque. So the gas turbine itself has to provide torque, but so we go for the shaft horsepower. Of course, there's still some exhaust and it's still producing some thrust, depending on the engine type, yeah, up to by around, let's say 10%. And as an engineer or constructor, you have also considered this little amount of thrust. So they are set or defined, yeah, shaft horsepower, SHP. And if you also consider the remaining thrust by accelerated air out of the exhaust, and this makes it the equivalent shaft horsepower, ESHP. I hope you remember this name. Yeah. So depending on the engine, skipping to maybe a helicopter engine, let me check here. There's one here. For example, a helicopter engine or an engine for a helicopter, yeah, we have absolutely no interest in any thrust produced by an exhaust. So we try to gain only shaft horsepower, yeah? And so we call it SHP. That means also that the turbine has to be designed to extract as much energy out of the accelerated gas as possible. And this is the biggest difference to our normal gas turbines producing thrust, where the turbines are designed to extract as much power, yeah, as necessary to drive our compressors. Yeah, please, yeah, bear or consider those mainly engine types. Yeah, those who provide just shaft horsepower, APU, or in this example, helicopters, compared to the engines that are just accelerating air. Yeah, shaft horsepower. Yeah. So here, yeah, as you can see also as an example, I'm sorry, yeah, we have here our reduction gearbox. Yeah, again, the turbine designed to extract as much as possible of energy, no interest, yeah, in any thrust by accelerated air. And here you can see also the combination, yeah, for example, the compressors. We talk a little bit about compressors later, yeah. But most important thing is the force that goes here into our output shaft, yeah, because there are our propellers installed, and then we produce our torque. Ramjet engines, not that interesting. Yeah, this was a theoretical idea from a guy in France called Laurent, who had the theory, one of the first guys, yeah, to build an engine just with the shapes, yeah, convergent or divergent shapes, but he could not prove it because it was the end of the 18th century, 19th century, sorry. He couldn't prove it because there was no material, yeah, just a theoretical idea. And also here, worth to mention, you know, when they started to try to standardize those engines regarding the so-called stations. Yeah, regardless the manufacturer, what is their idea? Idea was to separate an engine into different sections, and they call it stations. Of course, some stations are more important than the other ones. Yeah, and we discussed this while module 15. Yeah, the station number 3 is one of the most important ones because here, at this point, at the exit of the compressor, regardless if you have 2 compressors or 3, station number 3 is the exit of the compressor. At this point here, the compressor has maybe, hopefully, done its job and has a certain mass of air and a certain compression ratio. So we have a lot of potential energy. Therefore, station number 3 is one of the most important ones. Yeah, and the other one here, somewhere between 4 and 5, also this we come later on here. So number 4 is entering to the turbine, while number 5 is the station exit the turbine. And it's your daily work. Yeah, we call the so-called EGT probes or the measurement of our exhaust gas temperature. Sometimes, yeah, it's T4.95, sometimes T4.9. Yeah, we place, or the manufacturers place the EGT probes somewhere between entry the turbine and exit the turbine. And so therefore some strange names appear here, depending on the manufacturer, of course. Yeah. Talking about EGT, exhaust gas temperature, normally, to be fair, we should measure the turbine inlet temperature, the TIT, but since it was from the technology and materials some kind of difficult, the manufacturers start very early, yeah, not to measure the TIT, and therefore they place this somewhere here. It's much easier to place some EGT probes up there. And the last engine, or the newest, you have also in your fleet, the PW11, they put the EGT probes up here, yeah, in the turbine exhaust case. So this depends on the manufacturer. But officially, yeah, they have an interest to know the inlet temperature, and what they do is they measure the temperature somewhere here in the low pressure turbine, and when they measure there maybe 800 degrees, they know that the turbine inlet temperature must be about 1500 degrees. Yeah, this is the idea. Talk about, yeah, here, engine stations. Yeah. Zeros, ambient, yeah. There's 9 because normally it goes into including the afterburner, but this is not our issue here. Yeah. Engine stations. Here you see 9, which is okay. So oops, that's it. Fuel system. Nothing about compressors. I think the order in this handout, let me check. We have to go through some hardware here before we go into the fuel system. That's strange. Fuel control, this is near the end. There's something missing, I'm sorry. Strange. Okay. But your experience, you know most thing already. Yeah. Talk about compressors. You will probably remember there are 2 kinds of compressors. Yeah, there's an compressor builds designs. Yeah, we have radial compressors and we have axial compressors. Yeah. So the point is why there are 2 different kinds, and so both exist, so both make sense. Yeah, and just to remember you, yeah, the advantage of a radial compressor was and still is that the ratio, the compression ratio per stage is much better than the one from an axial compressor. Yeah. So with a radial compressor, you can reach 5:1, 6:1 compressor ratio, whilst the compressor ratio on an axial compressor is much worse. It's 1 to 1.3, whatever. Yeah. So, and that is also the reason why we have so many stages in an axial compressor. As you can see here, yeah, just an example. Yeah, we have to install so many stages right after the other because the compression ratio of the axial compressor is compared to radial very, very bad. Yeah. So, but the point is, why do we use axial compressors in our big engines? So, and this is a disadvantage of the radial compressor. The radial compressor is not able to consume as much air as an axial compressor because we have to re-guide, yeah, the air since it's radial, yeah, and so it does not make sense to have more than 2 stages after another. Otherwise, you have loss in energy because you have to redirect the air. So please bear in mind, yeah, that we find only or pure axial compressors, of course, in our modern new turbofan engines that consume a lot of air. So we have to deal or have to work with the axial compressors. APUs, for example, yeah, depending on the engine type and what is the task of the engine, we find mainly axial compressors, and some engines designed for helicopters, we have a combination of first an axial compressor followed by a radial compressor. This makes the engine consume more air, but you still save a lot of space. Yeah, so general build compressors, yeah, 3 different kinds or 3 normal kinds, radial, axial. Please bear in mind the advantages and disadvantages. And also the third version would be a combination of both. Yeah, and since we talked about compressors already and turbines, so our rotating parts, Yeah, and when we talk about let's say turbines, yeah. So maybe you do an test, yeah, after an engine has been installed on the aircraft, maybe the maximum power assurance, and you find something while it's your borescope inspection. Yeah, how was it? Was it the nomenclature of the turbines? How do you proceed? You have a failure, a dent, some damages in the third stage, for example. Why would you consider, or what do you name the third stage turbine? Or what does a stage consist of? Same with the compressors. Yeah. Please bear in mind that a stage, regardless the number of the stage, a stage in the compressor or in the turbine is always a rotor and a stator. Yeah. Of course, the compressor officially starts with a rotor followed by a stator. The turbine starts normally, usually with a stator followed by a rotor, but it can also name different. Yeah. So a stage consists of this. It's not separated in low and high pressure, whatever. Yeah. A stage consists of those two items. Yeah. Okay. Also coming back to compressors, because the compressor is very sensitive regarding stall, so they had to do a lot of things to avoid stall. Yeah, we have to make sure that the air is always, yeah, in movement through the engine. It is not allowed to stuck, or yeah, that the airfoils do lose the connection with the air, which means also stall. So one thing they invented is, or they had to invent is, the several shaft or the multiple shaft system. And another thing is, since they would like to reach more compression ratios with more consumed air, how to avoid stall, especially in the HPC, in the high pressure system. What was still there invented in the compressors?
Valve?
Yeah, what kind of valve? So we have, yeah, maybe you remember, I can also show you the example because it's very important. Let me check here. You will probably remember those animations I have. I make some. Just one little break here. We have systems. Here. Maybe you remember this one here. One solution was the so-called, in this engine type, they call 2.5 bleed, which is also a nice example for the station. Now we are after, yeah, the low pressure compressor. I skip a little forward. And before the gas is entering the high pressure compressor. So this is station 2.5, as they call it. You can see the animation. I hope so. Let's stop here. Yeah. So right in the behind this case, yeah, the low pressure rotors are and starters, or of course, are installed. Yeah. And at a certain moment, especially at engine start, let's say this way, yeah, it's better to relieve some air, some compressed air. We invested work, of course, yeah, but it's better to release some air here before the low pressure system puts too much air into the high pressure system, what the high pressure system at this moment is not able to consume. So therefore, we have to get rid of some air until the high pressure system has its optimum RPM and is now able to consume this mass of air, which is a low pressure system, yeah, is providing. And what they do is they just open here with an actuator. The tube, it's a bleed ring. It can be individual valves, whatever. So this is a VBV, yeah. The other thing I can unfortunately not show you, yeah, we have the so-called bleed valves here at the HPC. Yeah? On V25 engine, for example, they are clearly marked red. You can see it very clear. And on the PW11 engines, which you also have, there are just little ones. And the idea is, let's take over here, that you, especially for engine start, those valves are open, and it's got two reasons. Yeah. Reason number one, to make it easier for the starter to get the high pressure system on RPMs, and also to avoid that the air does stuck in the HPC. So this is two reasons. Therefore, we have also the HPC blade, bleed, yeah, because we have to control the flow of the air through the engine without getting the risk of a stall. And the other thing I would like to show you, also important, so how to manage to control the air through the engine. Now you should see this one here, and this is I put you a little forward. We have a so-called VSV system, variable stator vanes. Sometimes, depending on the constructor or the manufacturer, they call it, or they separate, unfortunately. Here we have the first stage, and since the air is now entering here, the HPC system, they call it inlet guide vane, which is some kind of confusing because it's still the same job. So the first stage in general is called VIGV. Please bear this in your mind. And then followed by, in this case, 1, 2, 3 stages VGVs or VSVs. Variable guide vanes or various stator vanes. That depends. All, in this case, 4 stages have the same job. I skip a little. You see the actuator is moving now due to the link, the individual vanes. Let's remove it. So what was the idea? The angle of attack is influenced by 2 speeds. One, the first speed is the speed of the rotation, so my RPM. And the other speed is the speed of the air through the compressor. And those 2 speeds make the angle of attack. In order to have the right angle of attack and to avoid stall, the angle need to be adjusted, and otherwise every engine would stall. Because that's why we find, especially in the high pressure system with high RPMs, we need those variable guide vanes. Also, I showed you the example with the PW11 engine, where they separated the RPM from the fan, from the system. So, and one advantage was now that the low pressure compressor was able to turn faster, turning now with 10,000 RPM compared to older engines that turn just with 4,000 RPM. But they need also now, in the low pressure compressor, variable guide vanes. I want you to bear in mind, if it comes to how do we control the flow of air through the compressor? We have our variable guide vanes, variable inlet guide vane, because the constructors call it though, or maybe also that the clearance of the blade will be adjusted. I personally have it's just older engines where they try to adjust the clearance of the blades. But consider this also, that in order to avoid stall, also the clearance, was controlled anyhow. We have to control the airflow through the compressor, otherwise we go the risk of a high stall. So therefore, we have those VGVs, VIGVs, and an automatic adjustment. And also, another thing was to avoid stall, those so-called bleed valves. so far? Yes, I think so. Yeah. Strange that it's not mentioned here in the handout. I will close this here, and also this here, and go back to 16. Thing here. So you're still awake? Are you still there?
Yeah, we're still here. Yeah.
Oh, very nice. Thank you. Yeah. Yeah, I'm sorry when I ask you something, and when you answer in the chat, I see it very late, so I'm sorry about that. Especially Yelan, I'm sorry. We had, yes. So the first little break after 1 hour as discussed. So, okay, just raise your hand. The raising hand is a nice one because it goes very fast. Let me check here. Okay, so I would suggest, is it okay, 10 minutes? So 10 past, what are we now? 10 past 2, is it 10 past 2 then? Fits? So I can grab a coffee, yeah? And we make, yeah, about 12 minutes.
Yeah.
Okay, see you then. I get myself a new coffee.
Перекур волнуется. Я.
Прием.
Угу.
Андрюх, ты записываешь, да, лекцию?
Сколько вопросов уже рассказал?
Что там, что происходит?
Алиш, сколько вопросов записал?
Я жду, когда кто-нибудь еще запишет.
Меня слышно, ребята? Раз, меня слышно? Меня слышно, ребята?
Кабина, как слышно?
Земеля, ответьте, Земеля. Әбітте біздің Алматы уақытында сағат 3-те.
Ben saat 12 demavuzun bir saat benim ben. Saat уже 2 oldu.
Солай шығар, иә. Вроде 15:00 қай немен? Сіз қай жаққа кетесіз? Қай жағына? Yok. Meni görüyorsun. Ha, iyi zaten. Hı? Koko? Koko çok. Ребята, меня слышно вообще?
Also to cool down our oils. We have a win-win situation here, and the fuel then passes the fuel or heat exchanger. Ice will be melted down, and after this, so after we have passed the fuel or heat exchanger, we will filter. It's always nice to filter because there may be some other things in the fuel when you recognize what they everything forget at the maintenance, whatever. So it makes sense to have a low pressure filter installed. Right after this, we have the high pressure pump. And also here, the high pressure pump will always provide more fuel as needed. Because this makes the reaction time faster in case that the engine has to enhance the fuel flow very fast. You maybe, whatever, think of TOGA, take-off, go-around, whatever. So the system is able to provide as fast as possible more fuel. That means also that the fuel that doesn't need it, will be redirected in the circuit, which is here, this graph here, So it will circulate within the system. Maybe there will be a moment when the fuel gets hotter and hotter, the not used fuel. It will be sent back also to the tanks. This is a motive flow here, but it's not that important for us. So high pressure fuel now applies high pressure and more fuel than we really need. And again, we send it through a filter. And then we entering this HMU. You can call it HMU, or other manufacturers call it a different way. In the HMU, the three things will happen. It will be measured, it will be governed, and metered. How many fuel do we now really have to send to the fuel nozzles? Of course, this also is, everything is influenced by the EC or the ECU. We come to this later. The most important valve here within the HMU is a fuel metering valve. The fuel metering valve, here you get those, here the line here, is of course controlled by the EC or ECU. And here now the ECU makes the decision how much fuel will be sent to the fuel nozzles. And this decision will be made here. And also to remember you, if the EC, ECU, or the FADEC system, it does not just order, it also need of feedback signals, because there must be communication. It's not enough if the ECU says, okay, now fuel metering open on this level, and does not know if the fuel metering valve did it so. So the feedback signal was a so-called LVDT. You will probably remember. And also how to make a valve move, or an actuator. There are two items, because I always compare it with the human body. We have our brain, which is the EC, but not just if my brain says, okay, I would like to lift my arm, nobody will react if there's no device that is acting. We need our nerves, that gives a signal to our muscles. So my brain says, move your right arm, whatever. EC says, okay, fuel metering valve, please open or close or move a little bit. So that will be done, with electrical harnesses, connections. And there are two things that transfer an idea, a thought, an order into movement. I introduced to you the so-called torque motors, how we now transfer a think or an order into movement. And the other one was the so-called solenoid valve. Please bear in mind, in order to make the system really moving, we need torque motors. So this is the idea or the task of the torque motor. So then the ECU or EC now orders the fuel metering valve to open, And now the fuel, yeah, this is a high pressure shutoff valve here. Then after this HMU, now the fuel would like to go to the fuel nozzles, and we find here the fuel flow transmitter or fuel flow meter. It's got several names, which is an indication to the cockpit. Of course, the cockpit also needs to know how much fuel will be sent now to the fuel nozzles. But please do not forget, it's the indication is just for the cockpit. It's nothing to do with the calculation of the EC or EC. Yeah, in order that the system knows how much fuel is used or sent to the fuel nozzles, the EC relies on the feedback signal from the fuel metering valve. Yeah, very important. Yeah. So then now we have the fuel flow meter or the fuel flow transmitter and indicating to the cockpit so they can calculate whether there's fuel on board or remaining fuel, whatever. And then the fuel passes also here. Sometimes there's an additional valve here in this graph, so we can skip this because the most important is the high pressure shutoff valve and then the flow divider valve. Valve, yeah, to manage to control, especially at the beginning when we would like to start the engine, we need less fuel for reliable startup. So the flow divider valve opens just one channel, one line to the fuel nozzles, whilst when the engine is successful started and we have now we would like to take off, for example. So we have a higher fuel demand. So the flow divider valve will open the second line. Yeah, here I'm primary and secondary named. And of course, if you have those two lines, you need two kinds of fuel nozzles. The ones are called duplex nozzles. So they have the ability also to provide fuel for the start sequence. They want to have two lines, whilst the main fuel nozzles just work and get fuel while normal operation starting from idle upwards until takeoff. Yeah, so this is the one thing. Fuel metering valve, very important. Yeah, and of course we need also fuel as an hydraulic medium to drive our actuators. Yeah, in this case here, my variable inlet guide vanes, my various data vanes, we have our 2.5 bleed, yeah, wherever we have an actuator that needs to be driven by fuel, and some all aircraft types for this have also an additional pump that overtakes the job of providing pressurized fuel. And I think it's Boeing, they have also an additional fuel heater here, but this is specialized especially for other fuel systems. So this is a simplified fuel system, yeah? Distribution, yeah? We come to this later, yes. We have a low pressure pump and we have our high pressure pump. And we have here, there's an example, it's a not so nice example for a fuel oil heat exchanger. And yes, which pressure is higher? The one from the oil or the one from the fuel? Do we remember? Oh, tell me. Azamat, I think we have said, I don't know. Regarding lunch. Whenever, let me see.
Yeah, I'm sorry. We said 15 o'clock or another
I
time?
think so, yeah. The decision of the team. So, okay. Yes. Okay. Good. I will take care and let me know if it's that far. Yeah. So, question. Yeah. Which pressure is higher, the one from the oil or the one from the fuel? And of course, if there should be a leakage in the fuel oil heat exchanger, it makes more sense to have oil in the fuel system because it just will burn than fuel in the oil system. Because if the fuel pressure would be higher and you have a leakage, then fuel would enter the oil system and will change, why? It will influence the oil, because I'm missing the word now, I'm sorry. So it maybe will change the behavior of the oil, so the oil cannot lubricate anymore, and then we have a very fast failure on the bearings, which can be not so nice and very expensive. So oil pressure here is slightly higher than the fuel pressure in our fuel oil heat exchanger. And yes, going back to oil, there are several coolers, because fuel just exchange the heat with the fuel is not enough. We find also air oil coolers. This is the advantage of an additional fuel heater. It's more mainly driven by Boeing, as far as I can remember, in their system. It's always nice to filter, and all filters have, of course, a bypass. Some filters, if it's important information, they have also the differential pressure switch that measures the pressures before and after the filter in order to have it displayed in the cockpit. Because if the pressure, the difference drops very high, it's an indication that you have a blocked filter. Well, this shouldn't be that important for us. HMU has many names, depending on the constructor or the designer, but it's all the same. I call it often also a slave, because the HMU has to convert the ideas, the orders from the EEC. So there are torque motors installed, and maybe also some solenoid valves, and it's providing also the pressure for the actuators, as stated here. Flow meter. As I said, for the calculation of the fuel flow, it's not exact, not detailed enough for the EEC. Therefore, it's just an indication for the cockpit. This is a flow divider valve, as can be seen here. Normally it's a spring loaded valve, because the fuel itself, as soon as the fuel enhances, the fuel flow enhances, the fuel automatically will open the second flow, because the valve here or the spring here will be pressed together, and then you have two flows. This is the idea of the flow divider valve. Older engines, you can find individual flow divider valves for all fuel, or for every fuel nozzle. Most engines I know, you have just now one flow divider valve, and for all following fuel nozzles. Fuel nozzles itself, we have to maintain, or we have to make sure that at the beginning we need a certain spray pattern to have a reliable start sequence. And as soon as the fuel flow enhances due to that we need more power, the fuel nozzles have to make sure that the pattern of the spray pattern, is as it should be. It's not allowed to go in this direction, because then you damage the combustion chamber. The spray pattern is not allowed to be too long, otherwise you damage the turbine. So it's a quite sensitive part. Fuel nozzles. Here, the advantage of the pattern here. At the beginning, we have a low flow pressure, and compare this with the end when we have the full fuel flow. Oh, very difficult. Fuel nozzles. HMU. There are several types. Engines of today, driven by the FADEC, they just transfer the orders into movement. We can skip this a little bit, not that important, because the idea comes later. What is very important here, if the FADEC, how the FADEC should work. Let me go this one here, this one graph here. LVDT. Yes, fuel control. So what is important now comes here. So with implementation of FADEC, they gave the engine the full authority, of course, since now it's not that much influenced by human beings. You have also to give the FADEC system more information. Yeah, that's also one reason why they invented more data out of the engine. Let me see, this one is better here, I think. I like this more. Yeah, so here's my brain now. It's, in this case, it's called ECU. Yeah, we have to allow, or we have to make sure that the ECU is doing the right decisions. Therefore, the ECU needs informations. Yeah, so we have to divide in so-called control signals. Yeah, we have monitoring signals. What's here? Control signals in general. Yeah, the T12, although it's not 12, it's 1.2. Yes, we have our sensors for the RPM, N1 and 2 in this case, so we have a two-shaft system. Yeah, we measure the temperature right after the low-pressure compressor, for example. Maybe we measure the static pressure. Yeah, you can see it's always the same, pressure, static, and then comes a number which defines the station. In this case, it's the static pressure at station 1.22. Then the most important thing here, because it's the job of the compressor to provide high pressurized air. So we have an interest after the compressor, which is station number 3, to know the static pressure. Yeah, we measure maybe the temperature on the turbine case, and also this is very important here. In this case, they call it T49.5. Of course, it's wrong. It's station 4.95. Yeah. So why is EGT so important? Yeah. Minimum two reasons. Yeah. At the one hand, the designers, the constructors of the engine define the EGT with a temperature where we go the risk that the engine gets destroyed. Yeah. First task of the turbine is to survive. Yeah. Before it extracts any energy. I told you this already. So we have to. Yeah. Therefore, EGT is limited. Yeah, engine does not need to be destroyed because it costs a lot of money. So therefore, EGT measurement is very important. And the second reason to measure the EGT is due to performance reason. Yeah, you can easily compare if you have a 2-engine aircraft and you see a takeoff or maybe also at idle when you observe the EGT. You can easily see which engine is newer, or in better shape, or in better condition. Because at the beginning, if an engine is new, all clearances within the engine are okay, are quite good. So the engine needs less fuel to gain the certain or the requested RPM. As soon as the engine gets older, the clearances also getting bigger and bigger. So the compressors need a little bit performance, and the turbines need a little bit loose performance. And the only way the engine can react in order to gain the requested thrust is to enhance the fuel flow. If the compressor, for example, does not reach the requested compression ratio, the engine will react by enhancing the fuel flow to enhance the RPM, so the compression ratio is reached. That gives you an indication for the performance. Yeah, though the older engine, the older the engine gets, the higher the EGT will be. And this is a normal reason also for replacement. Yeah, all engines will reach their limit with the EGT. you will probably also remember the name EGT margin. Yeah, the difference between the real measured EGT and the maximum allowance. For example, we have a new engine coming from the shop, maybe maximum EGT is 900 degrees, and the engine itself at takeoff has a EGT of maybe 820 degrees. So the margin is 80 degrees. The engine can deteriorate, yeah, by 80 degrees until he reaches his maximum EGT. Yeah, indication for performance, and also we do not destroy our turbine. Yeah. Next thing is, of course, the system needs to be independent from all other systems. So the EC needs its own power supply. And in general, we have here our alternator, which provides as soon as the starter starts to turn the N2 system and the gearbox, the ECU gets its own power supply. It is independent. Yeah. So then the engine takes care about itself, yeah, by variable bleed valves, variable stator vanes. So we do not go the risk of a stall. We watch the temperature and the HPT, and also the CC here is some kind of not quite right. Let's call it turbine inlet temperature. And of course, the fuel flow to the fuel nozzles. Yeah. So thrust reverser also, yeah, initiated by the cockpit, but the EEC then does the rest. Yeah. The starting sequence, as can be seen here, yeah, also, yeah, in the responsibility of the EEC or ECU. We come to this later at the end of the day. We talk also a little bit about starting. Yeah. So we have a lot of measurements, a lot of data, but this is of course not enough. In order to have a redundancy here in the EEC, we have two channels. Yes, channel A and channel B. So in fact, the EEC or ECU consists of two computers doing the same job at the same time. They get data, they collect data, they make decisions, and also they send signals to the actuators, also to the fuel metering valves, yeah, independently. What they but also do is they compare. Yeah, there's a device called comparator. So both channels A and B do the same time. They compare their results. Once there should be a deviation in the result, because there's just only one in charge. So A and B compare themselves and they find out, for example, oh, we have a different result. We make other decisions. This comparator now decides which channel is right, and then the channel which is right overtakes, yeah, and makes the decisions. So that's why they reach a safety in the system, yeah, by comparing itself and doing the right job. FADEC has been introduced end of the 80s, so some decades now, and it seems to work. Yeah, this is a theoretical idea. We do not go through this. Yeah. Indications already? No, it's too fast. I need more. Let's see. It's not okay. Okay, I switched to another presentation because, yeah, it's got a reason. You have to trust me here. Trust me, trust me. Let me see. So, it will be better if I show it you in another one. Let me see. So, I make it a little bigger. One moment. So, I hope it's big enough. Yeah, one thing I would like to highlight is, of course, the engine now, or the FADEC system, yeah, the pilot is still in charge and the pilot is still in command, yeah. Imagine the pilot says, okay, now we would like to lift up. That means now I need the full takeoff power. So of course the engine has to react and provide now the takeoff power. But before, the engine is not now enhancing the fuel flow blindly because it would go to the risk that the engine itself will destroy itself. And this is a graph here. Yeah. So imagine now, yeah, pilot is requesting for takeoff, the fuel flow, yeah, this so-called steady state curve here, that shows the optimum enhancement of the fuel flow. We have here, and the red one is our N2 system, the high pressure system, and our fuel flow. So pilot is just pushing the thrust levers to the front, requesting takeoff thrust. Yeah. Every engine, maybe it's an old engine and a new engine, yeah, they will act differently because not both engine will now enhance the fuel flow as possible. It's because it would be rubbish. Yeah. We have several risks. Yeah. If the engine would enhance the fuel flow too fast, it goes to the edge here with a compressor stall limit. Yeah. So also what can happen if the engine enhances the fuel flow too fast, we go to the over temperature limit. Remember, please, yeah, if 600 kilograms of air will be moved by the engine and we have a bypass ratio of 6:1, that means 100 kilograms of air enter the engine. About 20% will be extracted for other purposes out of the compressor. That means in the combustion section, just for an example, 80 kilograms will arrive. So from this 80 kilograms of air, just a quarter, 25% are used to be mixed with fuel and burned. The other, now 60 kilograms, are used to cool and protect the combustion section. If the engine would enhance the fuel flow too fast, there will be a lack of cooling air. Therefore, we go to in the risk of the over temperature. Yeah. So, or other failure, we go at over speed. Yeah. At this RPMs, especially for the N1, also fan blades do wait a little bit, and we cannot go the risk. And the turbines are more material, so more centrifugal forces. We cannot go the risk that we go in overspeed. Otherwise, we would have, yeah, maybe a blade separation. Yeah. So in this case, we talk about fuel enhancement. The engine has to first check what is my condition, how I am, what are my RPMs, what is my current fuel flow, what is my current EGT, and all this stuff. And then the engine will react. Please bear in mind, yeah, that if the cockpit requests an enhancement of the fuel flow because would like to take off, yeah, the engine will of course react, but always will consider, yeah, the actual RPMs. And this is important, yeah, because we talk about takeoff. It's according to N1, yeah, not N2 as mentioned here, because N1 provides most of the thrust. Yeah. So, and the metering valve is now taken consideration, whereas, yeah, I have to provide a certain N1 to have the takeoff thrust, but what is my condition? Yeah, without gapping, go the risk of destroy the engine. And this here, yeah, it also has to make sure that there's always a certain gap to the surge line. Yeah, you know that after stall comes surge. Yeah, first we have the stall and then comes surge. I'm sorry. Yeah. So this here, there must be a certain distance. Yeah, and also a safety distance. This gap here, in order not to destroy the engine. Okay. Very important. Yeah. And so yes, the metering valve will listen, will obey to the request of the cockpit, but without damaging itself. So the engine has to take care about itself. I will wrap it up after our day here and make it new, whatever. But you got the idea, I hope. Yeah. So I go back here. Let me check. Yeah. No, I will not. No, no fuel tank safety. Clearly, no. So, yeah, I think, let me check. Okay, good. Then we go to some indications here. Yeah. So I will pick the most important indications, of course. Yeah. Yes, about the exhaust gas temperature, I talked a lot already about, why it is important. Yeah. So there are many ways, to measure the EGT, which is of course a very healthy system. Let me check here. I would like to highlight. Yeah. From today on, or the most. Measurements of the EGT, although we should measure the turbine inlet temperature, but we concentrate, where we put here our so-called thermocouples. Yeah, how to measure the EGT. The idea is on most engines, we have a bimetal here, in this case, chromal aluminum element. So we have two different kinds of material. Yeah, and what happens if they heat up is they produce, voltage, of course, in the area of mini voltage, as can be seen here. So they found out that for about every 100 degrees Celsius, those so-called thermo elements will create 4 millivolts. So all you have to do now is to transfer this millivoltage, of course, in a higher voltage to have an indication in the EGT system. Yeah. So here, for this case, we have here the measuring junction, our thermocouple. Then the way of the measurement goes normally in a so-called junction box, because we have several thermocouples in the circumference. And there's here a balance wire, and then it goes into the indication. Let me check later on, which is more important here. Yeah, those are the thermo elements, as you know them from your engines probably too. They're quite cheap. They're just some little metal things. As far as for my history, whenever they were not functioning, we just scrap them and install new, because they're not that expensive. Yeah. Of course, what we have to make sure is, as you can see here, how first thing important is we do need an external power supply, because those chromal aluminum thermocouples, they produce their own voltage. So it's an advantage. You don't have to feed them to provide them with any power supply, which is also nice. So they're independent. But what you have to make sure is, maybe in case of repair of the wiring system, it's working also with resistance. So you have to make sure, if you have the wiring to replace, that you must use the same material in the wire. Of course, you work in accordance with the manual, but imagine you have here those thermocouples here. They produce now the millivoltage, and you use a different wire, with the other resistance than the original one. So the value, the measured value, will be another one, or a wrong one. Let's call it this way. Please consider this, or keep it in your mind. If it comes to replacement of the wiring, use the one that is requested by the manual. Otherwise, you will have a problem. And if one thermocouple fails, maybe here it's 1, 2, 3, 4, 5, 8. So For instance, for example, yeah, you have one thermocouple or maybe two, they fail. How to create, what circuit do I need so that the system, the remaining thermocouples that are still working, yeah, provide data into the junction box here, yeah? You have three options, yeah? You can put all those in series, you can put it in parallel, or you have a bridge circuit. And of course it makes sense, since they are quite sensitive, that you put it in parallel. I think you agree, yeah? Because then if you would put it in series and one fails, you have no signal to the junction box, yeah? Keep in mind, please, yeah, that the system circuit which is used is in parallel, yeah, for the thermocouples. Wiring replacement, yeah, use the same material because of the resistance of the material. Otherwise, you have a wrong value. We have several thermocouples in circumference of the case. In order to always get a result or a measurement, you have to put it in parallel. Of course, very, very important. Yeah. So the ITT, there are engines. Some engines also measure the interturbine temperature. This is mostly also for fixed shaft engines, where we, yeah, for turboprops, as far as I can remember, but should be it. Yeah. So good. 50. Okay. So you want to make lunch now? Because then I can use the time to check what we still have to go through. Are you hungry?
A little bit, maybe later, after 10, 15 minutes.
Yeah, but because then I can see, I can check what was my last or my item after the lunch. So because there are some deviations here in the handout. I also found out the last 2 or 3 weeks ago. For example, compressors, yeah, not mentioned here, which is strange. Then I can recheck what is important for you and maybe what is not in the handout, so that you're well prepared. So therefore I'm asking, yeah. With other words, I will need some time to take a look, yeah, what is the most important for you. So if you agree, or if it's okay for you, we can do now your lunchtime, and I make some little works here, which is most important for you.
Agree.
Okay,
Yeah?
agree.
Okay.
Up to
Most of you are at home?
No, I'm not at home.
Oh, okay. 45 minutes? Is it okay enough for you?
For me, no. For me, no.
It's not enough?
Yeah, I should go to cafe or some places to eat.
Okay, that's not good. You're far away. Okay, let's do it this way. We meet again quarter to, oh, my time, your time. Sorry. Yeah. Let's try 45 minutes. Yeah, I will check in 45 minutes, or quarter to 4. Is it 4 then? 10, 14, 15? No, quarter to 5.